This was one of the trickiest A-level further maths questions in 2024. The examiners said in their report after the exam that this question proved to be a challenge for most candidates, with many failing to make any progress at all in part B. Oh dear, that was worth 7 marks. Ouch. Let's make sure it doesn't happen to you this summer. Let's read through the question. It says, the figure shows the central vertical cross-section of a vase together with the measurements that have been taken from the vase. The horizontal cross-section between AB and FC is a circle with diameter 4 centimeters. The base of the vase ED is horizontal, and the point E is vertically below F, and the point D is vertically below C. Using these measurements, the curve CD, that's this one, is modelled by the parametric equations given here and here. We've got the interval for T here, where A and B are constants, and O is the fixed origin, as shown in figure 2. In part A, we're to determine the value of A and the value of B according to the model. How can we do this? Well, let's have a look at where A appears. It's in this equation for X. Let's think about what happens to X as we vary our values of T, the parameter. Let's think when T is 0, what would happen? If T is 0, well then we'd have here sine of 0, which is 0, and 3 times 0 is still 0. So when T equals 0, X equals A. Now any other value of T above 0 will mean that this part is positive and non-zero, so it'd be adding something onto A. So what I'm saying is that the smallest value of X on this interval for T is X equals A. Let's look at the diagram and see what that would be. What is the smallest value of X that we have on this curve? Well, that's at this point or this point, both the same, right? They're vertically above. And let's think about where the position of this vertical axis is on this diagram here. Well, it's cutting the vase into 2 equal pieces. So that's where our y-axis would be positioned. And we know that this length is 4. So this length here, the same as this one and this one, would be 2, half of 4. So therefore, A must be 2. What about the value of B? Well, B appears here in the formula for y. Let's think about how y varies as we change the value of t. Well, this time when t equals 0, well, cosine of 0 is actually 1. So we have when t equals 0, y is b times 1, which is just b, right? So after that, for any other value of t in this interval, in fact, cosine will get smaller. And in fact, at the very end of this interval at pi by 2, cosine of pi by 2 is 0, so y is down to 0. So y starts at b and then decreases down to 0, which is what you can see here. Y starts at some value here, and then the y value as we move along the curve is decreasing down to 0 at d. So really, we want b to be the biggest y value on this curve. Well, that corresponds to the y value of c. What is that? Well, have a look at the diagram on the left. What would the y value of c be? Well, it's this length. It's going to be 7. So therefore, the value of b in the equation here is going to be 7. B equals 7. Part B. Using algebraic integration and showing all your working, determine, according to the model, the volume of the vase, giving your answer correct to the nearest centimetre cubed, for 7 marks. So we need to find the volume of this vase. I'm going to divide the volume into 2 parts. The volume of the neck at the top and the volume of the body of the vase here. Let's think about the volume of the neck piece at the top. Well, that's formed from rotating this vertical line segment by 360 degrees about the vertical y-axis, which would be here. If we do that, we're going to form a cylinder because BC is a straight vertical line. So it's going to be a cylinder, and we can easily find the volume of the cylinder if we know the radius and the perpendicular height, which we do. We'll look at that later. So that's going to be volume number 2, but we also need to find volume 1, which is going to be the volume of the vase itself, the body of the vase. And that's going to come from rotating this line segment here by 360 degrees around the vertical y-axis. And we'll form some kind of 3D object like this. What's the formula for that? How do we find the volume of revolution? Well, when we rotate by 360 degrees around the y-axis, the formula is an integral. Pi times the integral of x squared with respect to y, where the limits are y values. How do I know these limits are 0 and 7? Well, if you think about the y value of d, that is 0, and the y value of c, as we saw earlier, is this height, is 7. So that's how I've got these limits here. Now, to do this integration, I'm going to substitute in x, which we've got here. And I'm also going to need then to integrate with respect to t, not with respect to y. So I need to change this dy into a dt. How do I do that? Well, I can use the equation for y that I've got here and differentiate it with respect to t to get this. And then we can use that to replace the dy with this part. And as I said, we're replacing the x here with its equation. So that's going in that slot, not forgetting to put it in brackets and the squared on the outside. Don't lose that square there. Now, one other thing that we need to take real care about is that now we're integrating with respect to t, the limits are no longer y values, 0 and 7. The limits must now be t values. So I need to know what is the t value that corresponds to the upper limit, 7. So when y equals 7, what does t equal? Well, I can use this equation for y to say 7 cos t equals 7. Therefore, cos t equals 1. And therefore, applying arc cos on this interval for t, we end up with t equals 0. So when y is 7, the corresponding t value is 0. What about when y equals 0? Let's consider that. When y equals 0, well, 7 cos t would equal 0, therefore cos t would be 0, and therefore t would be pi by 2 on this interval for t. So when y equals 0, the lower limit now becomes pi by 2. That might feel a little odd to you because normally when we're integrating, the larger value, the more positive value, appears at the top of the integral rather than at the bottom. But that's not the case here. We haven't made a mistake here. We have to keep the corresponding values in their respective positions. So don't swap these over. We leave it as so. What am I going to do next? Well, I'm just going to tidy this up by bringing the minus 7 out to the front here to be with the pi. And then I'm going to expand these double brackets, not forgetting the middle term. It's really important. Do it carefully. And not forgetting also that I've got a sine t on the end. Next, I'm going to expand the brackets, multiplying out to get this fairly intimidating looking integral. Let's think about what we can integrate already. Well, I can integrate this term. I know that would be fairly straightforward, but I'm not sure yet how to integrate this, nor to integrate this. The problem is that I've got a 2t here, but a t here, and it's the same issue with this one. So let's see if we can replace these sine 2t's and this sine squared 2t with something. You should know that sine 2t is 2 sine t cos t, so that can go in there. And if we square that, because I'm going to need that, squared, we'll get 4 sine squared cos squared. So I'm going to replace that in here. And if you do the simplifying, we'll end up with this integral that we have here. Now let's see what we can integrate now. Well, we can integrate this, that's fine. And we can also actually integrate this by inspection. How? Well, you should know that when we differentiate sine cubed, we get 3 sine squared cos t. And you can see here that we've got a sine squared cos t. So all I'll have to do is just divide by 3, and this part will then become sine cubed. But this final term is problematic, and that's because we've got a cos squared here, not just a cos t. So let's deal with this part. I wonder if there's another way to write this. So sine cubed cos squared. Well, I can split up the sine cubed into sine squared multiplied by sine. Why would I do that? Well, that would mean that I can replace the sine squared with 1 minus cos squared. And then if I expand the brackets here, I'm going to end up with something that I can integrate here and something that I can integrate here. So that's what I'm going to replace in here. That's going to go in that little slot, as you can see here. And now everything is ready to integrate by inspection. If you're not sure about how to do integration by inspection, well, I suggest that you have a look at the answer here and try differentiating it, and you'll see why it works, I hope. If not, perhaps I can do another video on integration by inspection in the future. So we've integrated, we've gone to square brackets with our limits here. We need to substitute in the upper limit first. Then we subtract, substituting in the lower limit of pi by 2 into here. And if you do the number crunching on all of that bit very carefully, you'll end up with this fraction. Not forgetting we've got this minus 7 pi on the outside. And if you do the number crunching again, you get this final answer for volume 1. Remember, that's just the volume of this kind of body of the vessel, of the vase. So we've got the volume of the body of the vase. What about the volume of the neck of the vase, this part? Well, we said earlier that when you rotate a vertical line 360 about the y-axis, you're going to end up with a cylinder. Hopefully you can see that this is a cylinder with a diameter of 4 centimeters and therefore a radius of 2 centimeters. And the perpendicular height of the cylinder is 4.5. So I can use the formula for a volume of a cylinder with those two measurements, 2 being the radius, be careful, not 4, 2, and the perpendicular height being 4.5. If you do the number crunching on this, you get 18 pi. So to finish this off, all I need to do is add together volume 1 and volume 2, and I'll end up with this. And then we need to read the question really carefully, once again, just to remind ourselves that we need to round correct to the nearest centimetre cubed. So if I put it in the calculator, I get this, and rounding appropriately, we get 426 for the 7th mark. What about part C? State a limitation of the model. It's only 1 mark. You only want to give one thing. Try to keep it simple. So some acceptable examples are the vase may not be completely smooth in real life. Or maybe in real life, the vase may not be symmetrical, as we've modelled it here to be. Maybe the measurements 7 and 4.5, 4 and so on might not be precisely accurate. Maybe the equation that we've got here might not be a suitable model for the actual shape of the vase. Maybe we haven't considered the actual thickness of the sides. Maybe that might affect the volume. And maybe, anything sensible really. Maybe the base might have a dimple in it. But there are some things that wouldn't be acceptable to say. You can read these through here. The mark scheme explicitly says that these possibilities would not score the mark.